Hello, I'm Gabriel Meyer-Lee, presenting on the selection of neural architectures in supernets. Here, we're referring to the end stage of supernet-based neural architecture search, where the final architecture is selected from the trained supernet. Through a brief survey of the literature, we see that overwhelmingly supernet-based neural architecture search algorithms utilize the selection method of the original DARTS algorithm, simply pruning the architecture to the desired size based on the magnitude of the learned architecture weights. There have been several studies examining alternative selection algorithms, mainly inspired by Bender et al.'s one-shot NAS algorithm. However, these methods typically strive to avoid interaction between the supernet training process and the architecture selection algorithm, seeking to train a supernet that can provide fair estimates of architecture performance. Now, we use a case study of a perturbation-based architecture selection algorithm in order to examine the effects of not considering this interaction from supernet training and architecture selection. Now, through a slight modification to the supernet design, we're able to mitigate some of the failure modes addressed by the perturbation selection method without perturbation and demonstrate a different relationship between this perturbation technique and supernet training. In order to perform a holistic study of architecture selection, we do a broad study of 5 supernet training algorithms combined with 5 architecture selection methods across several datasets and training durations in both the NASBench 201 benchmark space and the original search space of DARTS, which is shown in the right 4 columns. Now, the DARTS space results do indicate that pruning the architecture weights does discover the top architecture in each training context studied. However, in NASBench 201, we find differing methods able to discover the top architecture depending on the training context. Now, one interesting insight from the NASBench results is that zero-shot neural architecture search algorithms appear to be effective when implemented on top of trained supernets. Through experimentally separating the selection method from the process of supernet training, we see that zero-shot NAS algorithms, selecting based on either synaptic flow or Jacobian covariance, benefit from both the shared weights and architecture weights of the supernet in comparison to their use in their original context, essentially an untrained supernet. We also use the results of our broad experiment to evaluate competing explanations for the well-studied failure of DARTS on the NASBench 201 search space. These explanations are operation bias, specifically towards the skip connection operation, and discretization loss, which is error as the result of only evaluating superpositions of architectures and never individual models during training. Key to the study is the DARTS minus supernet training method, which modifies DARTS by including an auxiliary skip connection on the supernet to ameliorate operation bias. Viewing the weight assigned by each algorithm to the skip connection on the left, we see that this method does indeed mitigate operation bias. However, DARTS minus is still outperformed by the other 3 supernet training methods on NASBench 201. This can be explained by the discretization loss, which is viewed through the architecture weight entropy plots on the right. We see that DARTS actually reaches the lowest entropy of all of the training algorithms, which is a result of the erroneous convergence on the skip connection operation. So these results indicate that both of these explanations together can describe the failure of DARTS in the search space, but each explanation on its own is inconclusive. We can explain DARTS's improved performance on its original search space simply by examining the number of skip connections found in each of the final architectures discovered in our DARTS space experiments. This indicates that a larger number of skip connections is effective in this search space compared to NASBench 201, which may disguise the impact of operation bias. Finally, comparing broadly the rankings of the combinations of supernet training and architecture selection methods across each training context allows us to evaluate the relative importance of different components of the training context. We find that the search space the algorithms are evaluated in impacts the rankings the most, followed by the epochs each algorithm is trained for, and finally the actual set of data that is used to train and test each algorithm. Overall, These experiments provide a broad view of architecture selection, suggesting the promise of zero-shot methods used for selection within supernets, and elucidating the relationship between competing explanations for the failure of architecture weight pruning in NOSBench 201. Thank you.